this next lesson is going to give us an introduction to partial derivatives, and this may be a new topic for you if you've only taken Calc 1. A partial derivative is going to look at taking derivatives of functions in more than one variable. So what we've talked about so far are when we have y is equal to some powers on x, a polynomial in the variable x. Now we're going to look at what happens when we have polynomials in two variables. So sometimes we write this as z, sometimes we write it as a function of x and y instead of just x. Now we have our two variables, and again this is just going to be powers of x and y multiplied together. Sometimes they might also include just powers on x or just powers on y. And of course we can also end up with just a constant as well. So that's just kind of an example of how we would think about a polynomial. Again, coefficients, powers of x and y multiplied together, powers of just x, powers of just y, or just constants. And again, we are going to have this either labeled as z or as a function of x and y, and we can have numbers here for x and y if we're looking at an exact point. A partial derivative is going to take the derivative with respect to a single variable while holding all other variables constant. And what we're going to be doing here is we're going to be looking at things in three-dimensional space. So for example, if we have a shape like this, we might be trying to find out what our slope is. Again, derivative talks about slope, so we might be trying to find a slope along a certain plane. We can kind of move this around to look at it a little bit. We might be wanting to look at taking the slope over our x-axis here or over our y-axis here to try to figure out what it is that our rate of change is in a certain plane on a three-dimensional shape, which is what we're going to get when we have our variables, our function in two variables. Let's talk about notation for this. So when we talked about a derivative before, we had notation such as f prime or y prime or dy dx, again the derivative of the function y with respect to x. Now since we're dealing with two variables, we're going to change the notation a little bit. Instead of our dy dx, we're going to use what's known as a del. It's going to act on z, and we're going to take that with respect to whichever variable. So let's pick x first. Again, that means we're going to hold y constant. Another notation for this is f sub x instead of our prime. Now we are going to use this subscript of x to denote the derivative of our function z with respect to x, and similarly our derivative with respect to y is just going to be f sub y, and again this is going to be our derivative of z and shorthand with respect to y now. So again, we're kind of looking at those individual planes. And something to point out here, don't confuse the partial derivative with implicit derivative. Implicit derivative was good for related rates of change. This is going to be looking at rate of change in a certain plane. So what we're actually going to be doing, as I mentioned before, if we're finding the partial derivative with respect to x, then we are going to hold y constant. and we're going to differentiate with respect to x. If we want to find the partial derivative with respect to y, then x is constant, and we're going to take the derivative with respect to y. So this is actually a lot easier than implicit derivatives. So let's take a look at an example. So first things first, we want to take the derivative with respect to x here, so I'm going to use the notation the f sub x. You can use the del z del x if you want. Either one is fine. In this case, we're going to say, okay, derivative, we're going to, with respect to x, that means y is constant, so let's just bring it to the front like we do with the 5, write it down as a coefficient, and then we're going to take the derivative of x squared, which is 2x. Then we can simplify. 2 times 5, multiplication is commutative, so we can multiply those together. We end up with 10xy. Similarly, f of y, we're going to hold x constant, so we'll write that f5x squared down, and then derivative of y is just 1, so we simply end up with 5x squared. So if we were to actually graph this function, we would see that our slope, or rate of change, is 10xy along the x plane. I want you guys now to try an example, so go ahead and pause the video, try example 43, and then when you resume, we'll take a look at example 44. Go ahead and put your answer in the online system. Example 44, simply all we've done is now we have two terms. So in this case, again, f derivative of f with respect to x is going to be, we'll keep that y constant, so 2y squared, derivative of x is 1, plus derivative of 5y squared, well, y is a constant, so derivative of a constant is 0. So we simply just end up with 2y squared. F of y, on the other hand, we're going to keep the 2x constant, take the derivative of y squared, so times 2y, plus now we're going to take the derivative of 5y cubed, that is 15y squared. So simplifying, 2 times 2 is 4, we get 4xy plus 15y squared. So we're going to try another example. It's very similar. That first part is the same. The only difference now here is that we have 5x squared instead of 5y squared. So let's see how that changes our derivatives. In this case, we have f of x. Again, that first part's going to be the same. We're going to end up with our 2y squared because derivative of x is 1. Now the derivative of 5x squared is going to be 15x squared. So this is what we end up with our derivative of with respect to x. And now our derivative with respect to y, again, this first part's going to be the same. We've got our 2x times our 2y, so we end up with our 4xy. But now the derivative of 5x cubed is 0. So again, similarly, we got these same two first pieces. It's the second piece that's different for each of them because we had those different variables. So I want you to try this next example, 46, enter your answer in the online system, and that will conclude this video. The next lesson is going to look at some applications of partial derivatives.